Hello, Eastview Scholars. Welcome back. This is the third edition of Sharp Shorts where we talk about ionic compounds and how to name them. To this point, we've covered ionic compounds that have two elements and ionic compounds that have three or more. Those are the basic categories. Now we're going to look at a couple of, or at least one for now, specialty, which is transition metals. Okay. Transition metals, as we'll see in a moment on the chart, are those metals in the D block area, and they actually scatter down into the lower ends of the P block. If you think back to when we were calculating valence charges, we kind of avoided that area. As I told you, they do different things. The ions in the S block or the P block, there's one charge to them. Anions have one charge. You know that negative charge. Cations in the S block have one charge. They only drop one or two electrons. Transition metals have more than one possibility. So these aren't anything, this isn't a new or special type of compound. All it is either a binary or a ternary compound, which we've learned how to name already. But the cation, the very first element, is one of these transition metals. Okay. It's still cation, anion. It's still, compounds are neutral. You got to balance them out. The difference in those transition metals is they can have more than one charge, and therefore you have to somehow indicate which one you're working with. Okay. For example, iron can be a +2 or +3 charge. Is that going to change iron from being iron? No. But are those two going to behave and make compounds exactly the same way? No. So anyhow, here's what we're talking about. Here's the transition metals, and honestly, on this diagram that I found, you really should be including the trickle-down effect into this area also. Anyhow, they're in this D block. This is a better diagram. Metals with variable ions need a Roman numeral for charge. We'll get to that. But here is your transition metals. They span the D block and down into the P block. Okay. Why are they transition metals? Well, here I have the outbound chart we are used to for writing electron configurations. Here I have it set up as an energy diagram. And here I have copper. Copper has 29 electrons. And if you were just to follow this chart, 1s2, 2s2, 2p6, you would end at 3d9. And that is the final electron configuration right here. And here are my valence electrons right here. Okay. Now, if things were to stay this way, here's my outermost deal. And when I wanted to form an ion, I could drop those two, and I would become a copper +2. Okay. And there's nothing wrong with that. But with transition metals, because they have Ds, if you remember back when we were writing electron configurations, one of the questions was, how come 4s fills before 3d? And our answer was, the energies, as you can see, are between 5f and 4d, or 6s and 5d, or 5d and 4f. Those energy levels are not that far apart. Okay. And we said the 4s filled because it takes less energy to put 2 electrons in an s suborbital than it does to fill this one with 10. And so this will fill first and then come back here. Well, because of that proximity, it is more than possible that rather than filling the 4s, you initially fill the 3d. And in doing so, now my valence electrons here, my outermost shell, only has 1 electron, so when I drop that forming an ion, now I'm copper +1. Okay. And so for all these in the D block range, that's the possibilities. They can fill in a non-normal order. They don't have to follow this necessarily to the T and follow the order of this Aufbau chart because these are so close. they may not. And in doing so, that will change how many valence electrons they have. And in all reality, with some, as you look at them, and they can have 4 or 5 charges up to a +7 or stuff for like manganese, it's not that they lose the S, but transition metals can also drop some of their D electrons. And so it leads to variability. Again, we go to this, there's only 92 naturally occurring elements, and there's all sorts of billions of compounds out there. That leads to variability. And part of that variability is while those ions are the same, they won't necessarily act the same with certain deals, and with what they're bound to. And that leads to also naming issues. And I'll give you an example right here. So here's our explanation. They are binary or ternary ionic compounds with a transition metal as the cation. Transition metals are those metals starting in the D block and including some metals in the higher orbitals of the P. And they have more than one possible ionic charge due to the fact that those energy levels are very close. You may have partial filling for stability, and that changes your S and D and the electrons that you can lose. In the written wording here, then, as you can see on this copper nitride example, what I have to do is indicate the charge. What is the charge of that cation I am working with? Okay. How do I know which one I have? Okay. And then I would indicate what that charge is. And the exact problem is shown right here. These two compounds are both made of iron and oxygen. They both are binary, and I would name them iron oxide. But as I look at them, I can tell that they are not the same compound. Okay. This has 2 irons for every 3 oxygen, and this has 1 iron for every oxygen. They're both iron oxide, but they are going to behave differently in reactions. Okay. So the naming of the formula was the same, iron oxide, ID ending, because it was binary. What I have to do now, though, is figure out and put in the middle between the cation and the anion. I take a parenthesis, I put it in the middle, and I'm going to fill it with a Roman numeral that indicates the charge of one of those compounds, just one. Okay. So how do I do that? Well, there's one thing I know. Okay. Transition metals are metals. All metals are cation. They're always positive. So one thing that I can infer from that is anions, in this case the oxygen, will never change its ionic charge. So here I have I have 1 oxygen in this compound. Okay. That oxygen has a charge, 1 oxygen times a -2 charge means that I have a -2 component to the anion half here. I also have 1 iron. What I need to know is its charge. Okay. And multiply that by the number of atoms I have to get, well, this has to be +2 so that these can equal 0. Well, the only way that can be a +2 is if this one is +2. So the charge, this, technically, the compound is iron 2 oxide. Well, what about the one below it? And you may have already done the math in your head, and that's okay. Here I have 3 oxygens. Each one is giving a -2 charge. That's an oxygen, 3 oxygen. Each one is given a -2 charge for a total charge of -6. My positive charge is going to have to equal 6, so that added together those two equals 0. Well, I have 2 total irons times some number is going to equal 6. Well, that has to be 3. So this is iron 3 oxide. So the naming is just naming it as you would any other binary, or in this case here a ternary compound, but in the written words you need to indicate what the charge of one, and just one. This indicates the charge, the positive charge of the cation. It is not, I repeat, it is not the subscript. Okay? It's the charge. Let's do this example. I've got copper nitrate. IT tells me that this is a polyatomic. My copper is the first element, that's my metal, but it is a transition metal. So it's going to have one of two possible charges. Well, what charge is it? It's the 2. Nitrite, if I look on my polyatomic sheet, is NO2 with a -1 charge. Okay? And if I do my charge flip-flop and put in my parentheses, then I know the formula for this compound is copper to nitrate with a 2 right there for my charge flip-flop. Okay? What would be incorrect is to assume that when I see that 2, that I believe that that's the subscript. No. No. It is the charge of one of those atoms, and then I just have to charge flip-flop and balance it out. Okay? Anyhow, so that's transition metals. They are not any different than the other binary and polyatomic that I've worked with, except they are in that D block. Now, you are not required to calculate what that charge is. Again, on your Eastview cheat sheet, right next to the polyatomic is a box that says metals, transition metals. That gives you a selected number of transition metals, not all of them, but ones that we work with that are very common, and the possible charges that are very common for them. Okay? So practice up and scholar on, Eastview.